Students, our next topic is magnetic field due to current through a very long circular cylinder. Magnetic field due to current through very long circular cylinder. Consider an infinite long cylinder of radius r with axis xy. Let I is the current passing through this cylinder. A magnetic field is set up due to current through the cylinder in the form of circular magnetic field lines. The center of these circular magnetic field lines lie on the axis of the cylinder, and these lines are perpendicular to the length of the cylinder. Now we will calculate magnetic field at a point P due to current through the cylinder. Now the first case, when point P is lying outside the cylinder. Let small r is the perpendicular distance of point P from the axis of the cylinder. So here small r is greater than capital R. This r is greater than radius of the cylinder. Let B is the magnetic field induction at point P. This will be acting tangentially to the magnetic field line at P. This magnetic field will be acting tangentially to the magnetic field line at P, and this will be directed into the paper. This will be directed into the paper. Here B vector and dl vector, they are acting in same direction. B vector is the magnetic field at point P and dl vector is a small line element of the closed path. Now applying Ampere's circuital law, B dot dl integral over the closed path is equal to mu naught I. As B vector and dl vector, they are acting in same direction. Therefore this will be b dl cos 0, as cos 0 is 1. Therefore we can write this as B integral of dl over the closed path is equal to mu naught I. Now integral of dl over the closed path is equal to 2 pi r, which is equal to circumference of the closed loop of radius r. This is equal to mu naught I. Therefore B is equal to mu naught I upon 2 pi r. Therefore B is inversely proportional to r. This is the magnetic field at a point outside the long circular cylinder carrying current. Second case, when the point P is lying inside the cylinder. When the point P is lying inside the cylinder, then here r is less than r. Capital R is the radius of the cylinder, small r is the distance of the point P from the axis of the cylinder. Here r is less than radius of the cylinder. We may have two possibilities. If current is passing only through surface of the cylinder, which is so if the conductor is a cylindrical sheet of metal, then current through this closed path L is 0 because current is only passing through the surface of the cylinder. Now by Ampere's circuital law, B dot dl integral over the closed path is equal to mu naught I. As I is equal to 0, therefore this is equal to 0. Therefore B is equal to 0. Therefore magnetic field is 0 at a point inside the cylinder if current is only passing through its surface. Second, if current is distributed uniformly throughout the cross section of the cylinder, if current is passing through all the surface, if current is passing throughout all the cross sectional area of the cylinder, then current through this closed path L will be I dash is equal to I divided by 4 pi r square into pi r square, because area of the cross section of the cylinder is pi r square. Therefore over an area pi r square, current passing is I. Over area 1, current passing is I upon pi r square, and over the area of this is pi small r square, and over the area pi r square small r square, current will be I upon pi r square into pi r square. Pi cancels pi, this become I r square upon r square. Now applying Ampere's circuital law, B dot dl integral over the closed path is equal to mu naught mu r I dash. It is to be noted that if there is free space between the current carrying wire and closed loop, then B dot dl is equal to mu naught I. But if there is some other material between this closed loop and current carrying wire, then this becomes mu naught mu r I dash. Here mu r is the absolute magnetic permeability of the material of cylinder. Now B dot dl integral over the closed path, this become B into 2 pi r is equal to mu naught mu r in place of I dash putting this value. Therefore B is equal to taking this to another side, this become mu naught mu r I r square upon r square, and in the downside is multiplied by 2 pi r. Cancelling common factor, this become mu naught mu r I r divided by 2 pi r square. As mu naught mu r I 2 pi r, these are all constant, therefore B is directly proportional to r. Therefore for a point inside the cylinder, B is directly proportional to r. When we plot a graph between magnetic field induction B and distance from the axis of the cylinder, when I plot a graph between magnetic field B and distance from the axis of the cylinder for current through a long circular cylinder, then we obtain a graph this. This means within inside the cylinder B is directly proportional to r, and outside the cylinder B is inversely proportional to r. Therefore magnetic field is maximum at a point on the surface of the cylinder carrying current. Magnetic field is maximum at a point on the surface of the cylinder.